So let's get started. It's a pleasure to have Professor Manikandan Mathur from IIT Madras today as a speaker. So he did his BTech from IIT Madras, his master's from JNC Bangalore, then he did his PhD from MIT. And he has interest in many things many topics of turbulence, including stability-stratified flows, rotating turbulence. So he will tell us about polydispersal droplet size growth in turbulence. Okay, Mani, all yours.
Thank you, Professor Mahendra Verma and the other organizers for giving me this opportunity. I'm glad to be presenting some of my work on turbulent flows here. So it's not on rotating or stratified flows in this seminar, but yeah, this is another aspect of turbulent flows that we've been studying. So it's polydisperse droplet size growth in turbulence. This is based on the PhD thesis of Shyam Kumar, who has recently graduated, and my colleague S.R. Chakravarti and myself were joint PhD guides for this thesis of Shyam Kumar. So it's based entirely on his experimental work for his thesis. Okay, so our to start with, the particle dynamics in a turbulent flow is relevant in a wide range of applications, as we all know. So some examples are shown here, essentially highlighting the fact that the range of time and spatial scales can be quite wide. Shown here at the top is an example of a blood flow. Then it's relevant for fuel mixing in internal combustions, like volcanic eruption and warm rain initiation, which is the problem which I will spend a little more time on. And even very large-scale phenomena like planet formation. It's believed that particle dynamics or particle collisions in background turbulent flows is quite important. So I'll spend a little more time motivating my problem with the warm rain initiation problem. So to quickly summarize, what happens in warm rain initiation is there are these cloud condensation nuclei that form, and the increase in the size of the droplets up to around 30 microns is explained reasonably well by condensation. When I say explained reasonably well, is that you have to be able to explain the time it takes from the cloud condensation nuclei to be formed to when actually rain occurs. So this acceleration of the droplet size from very small to around 30 microns can be explained by condensation. Similarly, when the droplets become of sufficiently large size, let's say of the order of 80 microns or more, then because of the polydisperse nature of the droplet size distribution, different droplets are settling at different velocities, and this itself would lead to collision between these droplets and ultimately coalescence to result in an average droplet size growth. So droplet size growth beyond 80 microns up to the levels required for precipitation can be explained using just simple gravitational settling mechanisms. But somewhere in between, this is sometimes referred to as the bottleneck region. That's what is indicated in the graph here. It's not obvious what would be the physical mechanism that would lead to a sufficiently fast growth of the droplet diameters from 30 to 80. As I said, the gravity-based mechanism is not very efficient if the droplets are too small. So the turbulence in the background airflow has been suggested as one of those mechanisms that could explain how you can have accelerated droplet size growth from around 30 micron sizes to something around 80 or so. That's the problem of interest to us. So when we got started, we started thinking about how exactly does the properties of the background air turbulence influence the rate at which droplet sizes grow on an average. This is a well-studied problem. It's been studied for more than a few decades. And if I can, with a limited amount of time, provide a quick summary, there are two main mechanisms people think of when they think about how droplets could collide and coalesce. First is preferential concentration or clustering, essentially resulting in spatial inhomogeneity in the local number density. So regions where clustering occurs, you could imagine that the local droplet number density becomes large, and it could aid enhanced collisions, at least That's why it is studied as one of the possible mechanisms. A second is people think about what are the relative velocity statistics between particles. This could be between particles of similar sizes or particles of different sizes and so on. And there are more physical mechanisms that are discussed, which would either aid or deter these preferential concentration or particle relative velocity. What we did in our work, before I talk about our work, let me also highlight that one of the main non-dimensional parameters that's going to govern the dynamics of these particles is the Stokes number. And the Stokes number for a particle can be thought of as a ratio between a particle time scale to the background air turbulence time scale. In this definition, it involves the particle and the background fluid density. Similarly, it also involves the diameter of the particle to a length scale present in the background air turbulence. Here, it's the Kolmogorov length scale that has been taken. And depending on the Stokes number associated with the particle, the dynamics can be very, very different. For example, if Stokes number is much smaller than 1, then the particles would essentially behave like tracers, where they just locally follow the fluid flow, the local fluid flow. But if Stokes number is much larger than 1, the particle velocities could be very different or decorrelated from the local flow field. And again, the Stokes number of the order of unity, it's been discussed as regime that's conducive for clustering and so on. So my main message here is that the particle Stokes number plays an important dynamical role in their dynamics. Okay, so when we started off, we just said I want to take an overall average, overall characteristic of background air turbulence and think about how the droplet size growth rate is influenced by this turbulence characteristic. And the simplest we could think of was the turbulent intensity itself. Some of you imagine that larger the turbulent intensity, the more vigorous would be the relative velocities or the particle velocity fluctuations that could potentially lead to larger, at least particle collisions. But it's a separate question as to whether particle collisions will result in coalescence. That's a separate question. And as far as the rest of this talk is concerned, I'm going to focus almost entirely on particle collisions and say that particle collisions essentially would suggest a larger growth rate. So in some sense, saying that the process of collisions to coalescence is highly efficient. Not necessarily true, but let's please live with that for this seminar. Okay, so what are the gaps in literature we found? One of the important aspects in the rain problem or in many other real life settings is that you have a large distribution of droplet sizes in any application. So that's what we refer to as polydispersity. And several studies on the relative velocity and the clustering mechanism that I mentioned in a couple of slides back, they are focused either on monodisperse particles, where all the particles are of a similar size, or near monodisperse. So the particle sizes are not too different from each other. We are going to focus on the regime where you have a wide range of Stokes numbers that are present in our flow field. Okay, and the second aspect is, while I discussed the clustering and relative velocity as two different mechanisms, it's not obvious that they are in operation independently. There is likelihood that they are coupled, they influence each other. So we are going to look at a scenario where both are present. We are not trying to separate the two effects, but looking at the overall effect on the droplet size growth rates. Second, as I said, the effects of turbulence, background air turbulence. Let's say we choose specific air turbulence characteristics and look at its influence on the droplet size growth rates. That's the kind of question we are interested in. And it's a complex problem simply because a huge range of length scales are involved. First, the turbulent flow itself contains a large number of length scales. Everyone knows it's highly intermittent at smaller length scales. And an added length scale comes from the droplet sizes themselves. And in a polydisperse flow field, droplet field, you have a wide range of the droplet sizes themselves. So we are going to simplify the problem in some sense. Let's say all these individual mechanisms are present, but can I just ask the question of how does the droplet size growth rate or droplet collision rate depend on the turbulence level. Instead of turbulence level, I'm just going to talk about the turbulent intensity. And we all know turbulent intensity is strongly related to the length scales that are present in the turbulent flow. So in some sense, yeah, all these mechanisms I've talked about a big picture question that we are asking, which is how does the droplet collision rate or droplet size growth rate depend on the turbulent intensity? And this is an experimental piece of work. So that's another reason why we were quite excited to do this. Always wondering if we could set up a cloud-like situation in the lab. So this is a first baby step towards doing that. So the three main objectives were, can we design and assemble an experimental setup to investigate polydisperse droplet size growth in a turbulent airflow? The second is, yeah, let's say we fix the droplet field characteristics. Can we study the effects of the background air turbulence characteristics? And finally, maybe based on what, in fact, these were not the three problems that we identified in the beginning, but based on what we learned from this problem of effect of background air turbulence characteristics, we went on to fix the air turbulence characteristics and said, let's study the effects of the initial droplet field characteristics. Turns out both are important. So I order by first introducing the experimental setup and how we try to quantify the various flow field characteristics, and then these two problems one after another. So this was a vertical wind tunnel so the turbulent airflow is pressure driven, and you have these honeycomb structures and the converging channel to ensure that the turbulent flow that you have here is there is spatial inhomogeneities are removed, and whatever little turbulence is present is also isotropic to the extent possible. But then we have control over the air turbulence that we have generating by introducing this active turbulence generator at the downstream end of this vertical wind tunnel. So that's what I have indicated here. The active turbulence generator is essentially a set of oscillating vanes. I'll show you a zoomed in picture of this generator in the next slide. And downstream, so the uniform, more or less uniform flow goes through this active turbulence generator. We have achieved a desired turbulence intensity in this flow field, and then we introduce a droplet field via this spray nozzle that is indicated here. In this picture, the x-axis indicates the axial direction. So in my subsequent plots, when I refer to the axial direction, it's along the flow axis, and the transverse directions are y and the z-axis. But for the purposes of my results, we assume a transverse uniformity of the flow field. So which means we will go sufficiently far from this near nozzle region to achieve this uniformity in the transverse direction. I will talk about the measurement devices in a couple of slides. So this is
one quick question.
Yes.
The velocity field is air. Is it air is coming in, which mixes
that's
water?
Right.
So there's a wall there. So wall will block the air, no? Below the. So how does air and water mix?
No. This is not a wall.
Oh, this is not a wall. I see. Okay.
This is just an outlet. Sorry if it indicates it's not a wall. Okay. This is just an opening, and you have a free jet that's coming out of this vertical wind tunnel. So if there was no spray nozzle, this would just be a free jet. Is that okay?
Yeah, please go on.
Yeah. It's a good point. Maybe we should not have drawn this solid line here. Maybe we did that to indicate some dimension. I think we put that there to indicate a dimension. Okay.
No problem.
And so you have this background airflow and a droplet field, water droplet field from the spray nozzle. So this is the active turbulence generator. So it's active because we have moving parts in it, and we can control the turbulence characteristics via changing either the amplitude or the algorithm that drives the oscillations of these different vanes. There is a randomization going on in determining the movement and amplitude and phase of each of these vanes. I won't go into that details. There are more details available in this reference here, or please get in touch with me. I'll be happy to share more details of this specific device in our department. The assumption is that it produces near isotropic, it's not fully isotropic, and homogeneous turbulence. We'll discuss some of these characteristics in the subsequent slides. Okay, so what do we have in the near field of the spray nozzle? So let's say the spray nozzle is here at the location that I'm indicating. You have a primary and a secondary atomization zone. So this is kind of the region where the secondary atomization happens. The liquid sheets get broken down into water droplets. And in this near field region, it's a conical spray, in the sense that the droplets would be present primarily in an annular region. But once you go sufficiently far from the spray nozzle, the droplet field becomes more and more uniform in this transverse direction. And that is the region where we will focus on or make our measurements, because we are not interested in this transversely non-uniform droplet field regions. And the spray nozzles we have worked with generate droplet sizes in the range of 0 to 120 microns. And this field is introduced after the active turbulence generator. Okay, so very quick mention of the measurement techniques. There are primarily 3 different measurement techniques we adopt. The main one is phase Doppler interferometry, which essentially measures droplet sizes and velocities at a specific spatial location. So you have something like a probe volume. This can measure droplet sizes and the velocities of the droplets that pass through this probe volume. And we take measurements till around 30,000 droplets pass this probe volume, so that we can generate robust statistics. That was to make measurements of droplets passing through a single location. Yet another method that we used was to photograph a region that is slightly wider in spatial extent, of the order of 300 by 300 mm along the. So this is 300 mm by. No, it's not 300 mm. I'm sorry. It's around 5 mm by 5 mm region. I'm sorry for the confusion. So that will be like a square region that's somewhere here. Okay, and again, the x-axis is along the axial direction, and y indicates the transverse direction. And you use a kind of a microscope, so that you are able to focus on very small droplets within this 5 mm by 5 mm spatial area. So then you capture several droplets in the same picture, and you can visualize droplet collision and coalescence events. Finally, we also performed laser Doppler velocimetry in the absence of the water droplet field. This is so that we could characterize the air turbulent flow field without the droplet field. Because we are in a regime where introduction of the droplet field does influence the turbulence itself. So we wanted to characterize the turbulence without the influence of the water droplet. Okay, so I divide my talk into the results into 2 parts. First, we fix the initial droplet field. In other words, we fix the spray nozzle that's generating the water droplets. We fix the pressure difference and the mass flow rate through this spray nozzle. So the initial droplet field, the size and the velocity characteristics are fixed, and we just systematically change the turbulent intensity of the background airflow. So these results are now recently published in Physical Review Fluids. Please get in touch with me if you're interested more after listening to these results. Okay, so we change, as I said, we fix the droplet field characteristics at the initial from the spray nozzle, and change the turbulent intensity. As we go from experiment number 1 to 14, the turbulent intensity increases from around 8.5 for the smallest value to around 15.8 for the largest value. What is indicated in this column is both the turbulent intensity as measured by LDV. LDV is done, or the laser Doppler velocimetry is done without the water droplet field. And PDA is based on the turbulence intensity estimated based on the velocity that we measure from sufficiently small droplets. Because PDA will measure all the droplet sizes. So we selectively filter, we estimate the statistics or the velocity fluctuations just based on droplet sizes that are smaller than 10 microns or so, and assuming that they will be sufficiently close to the actual airflow turbulent intensity itself. And so what is shown in this column U and omega are the parameters that we change to achieve different values of the turbulent intensity. So U indicates the mean airflow velocity in the wind tunnel, and omega is the angular velocity, maximum angular velocity we provide to the vanes of this ATG. Through a combination of the two, we are able to achieve this range of turbulent intensities. And as I said, the flow field generated is nearly isotropic, but not fully so. You do see the values. It's of the order of 4% to 17%. This is the ratio of the velocity fluctuations in the axial direction to the and the velocity fluctuations in the transverse direction. But we are going to, I think it is well founded, we're going to assume that the anisotropy is not playing a critical role in the final results that we are reporting. And this will be of interest at a later point as we go from experiment 1 to 14. As the turbulent intensity is increasing, the corresponding Kolmogorov length scale is decreasing from around 330 microns to 130 microns. And let me recall that the droplet field itself, right at the spray nozzle location, is in the range of 0 to 120 microns.
I didn't understand L by LPDI. That's what is that?
No, it's not a ratio. I'm sorry. This is not a ratio. And I is the turbulent intensity that you measure by laser Doppler velocimetry, which is performed without the water droplet field. What you do is the water droplet field is not even introduced. You seed the airflow with very small oil droplets, but they're all going to follow the flow field. And you essentially do a particle image velocimetry on the oil droplets to estimate the turbulence intensity when the liquid or water droplet field is not present. The second one is with the droplet field. So it's the water droplet field, and PDA is used to estimate, measure the water droplet sizes and velocities. From that collection of data, what we do is to choose only those droplets which are 10 microns or lesser, assuming that those droplets will be more or less faithfully following the local airflow. And then we estimate the turbulent intensity from those statistics. So these two different values are from two separate experiments. The one on the left is without the water droplet field. So it's just the background air turbulence that we generate in the absence of the water droplet field. And the values on the right are the actual measured air turbulence intensity. So clearly they are different. The droplet field is influencing the air turbulence itself. Is that clear?
Yeah, but why is it increasing? Our with droplet it is more than without droplet, no?
Very good question. So in fact, you will see that the trend is actually reversing. In the first few experiments, you will see that the background air turbulence without the droplet field is larger than the turbulence intensity with the droplet field. Okay. And if you go to the later experiments, if the trend is reversed, its I is actually smaller than IPDI. I will talk about it at a later point. Okay. So thanks for pointing it out. Okay. So it's not just a single trend. For the first 6 or 7 experiments, I is greater than IPDI. And for the last 7 experiments, or the last 6, these, from starting from experiment number 10, you have I being lesser than IPDI. That has to do with the way in which the water droplet field is influencing the background air turbulence. Okay, so these are measurement from a single sample experiment. What you do is start measurements at an axial distance of 200 mm from the spray nozzle. And as I said, we are going to focus on the region in which there is in the transverse direction, there is no variability of the flow. And that's evident here. This is the mean diameter. These are based on the phase Doppler interferometry measurements, PDA measurements. And you're plotting the mean diameter as a function of the transverse coordinate y. 0 indicates the center of the spray. And you see that this is more or less invariant in the y direction from at x equals 200 mm. Okay, if you had made such a plot from a region that is much closer to the spray nozzle, you would see large values only in some annular region. So a finite width in the negative y and the finite width in the positive y region, with the central region being devoid of any droplets. But then we have moved sufficiently far from the spray nozzle, and now we have more or less constant mean diameter or droplet field characteristics with respect to the transverse coordinate. And then we make these measurements at several axial locations. So as x is increasing, you are going further and further away in the axial direction. And the obvious point to report here is that the mean droplet size or diameter is increasing with the axial coordinate. So then we said, hey, let's take a mean of all the droplet sizes across the transverse coordinate. So construct a capital DM, which is the mean droplet size representative of a given axial location, and plot the mean droplet diameter size as a function of the axial location in a given experiment. So this is all for fixed droplet, initial droplet field characteristics and a fixed turbulence intensity. So this is one of those 14 cases that I listed out in the table. And you clearly see systematic increase in the mean droplet size as a function of the axial distance. We were interested instead of the axial distance because there is a mean flow in the axial direction that is present in the background airflow. So we convert the axial coordinate x to equivalent droplet residence time, which essentially is a measure of for how much time the droplet has experienced the background air turbulent flow at different axial locations. So we just it's a very straightforward conversion from the droplet residence time to the axial coordinates, because there is a mean velocity that is associated with these droplets. So we just do distance by time equals velocity to estimate a droplet residence time on the x-axis. So so in some sense, this is where we are starting off. This is x equals 200 mm. And at that point, you have an initial droplet field at TR equals 0. And then as the droplets spend more and more time in the background airflow, their average size is increasing. So then you can define a droplet size growth rate as the rate of change of the mean droplet size with respect to the time for which it has resided in the background air turbulent flow. That's what we define. So we fit a straight line to this graph, estimate the slope, and we repeat such measurements for all the 14 cases that I listed out in the table. Are there any questions? Because this is the primary quantity that we are going to comment on. If something was not clear on this droplet size growth rate, I would like to address it now. Okay, so I will proceed. We plot this droplet size growth rate on the y-axis as a function of the airflow turbulent intensity. So these are the 14 different cases that I listed out on the table. And our intuition to begin with, we just said, hey, more the turbulent intensity, more is going to be the droplet size growth rate, because we were just expecting that there will be more droplet collisions as you increase the air turbulence intensity. So indeed, the droplet size growth rate increased as a function of I, but then we were trying to reach as large a turbulence intensity as possible in our facility. And it turned out there was an optimum turbulence intensity for which this droplet size growth rate was maximum, okay, beyond which it started decreasing as a function of I. This was a surprise for us. In hindsight, not so surprising, but when we were doing the experiments was a surprise. But it was a positive surprise because we had something to work on. So this is and you'll notice that the droplet size growth rate has increased by a factor of around 3, with just a turbulence intensity change from around 8 to around 11.512. So that is also an appreciable increase. So I want to point out both this appreciable significant increase in the droplet size growth rate and the fact that beyond an optimum value, the droplet size growth rate seems to decrease as a function of I. This is in some sense the main result, and we are trying to explain these observations. I should also point out that we have been very careful in estimating an error bar. We have been also quite careful in estimating the residence times, and this trend of the existence of an optimum turbulence intensity is quite robust. There may be some changes in the actual values, but the presence of an optimum turbulence intensity was quite robust. So then we said, is there a way in which you can estimate droplet collision rates based on the PDA data that we have collected? Turns out we can do something approximate. So we estimate the overall droplet droplet collision rates based on a few different theoretical come empirical relations. It is essentially separated into droplet collisions due to the air drag and droplet collisions due to the background air turbulence and the droplets having different dynamics in the background air turbulence flow. And these expressions are thanks to these two papers that I've indicated here, Safman and Turner, who mainly gave this estimate for very small Stokes numbers, and Abrahamson, who gave this estimate for very large Stokes numbers. So we're going from tracer-like particles for very small Stokes numbers to strongly inertial droplets for very large Stokes numbers. So as you will see, for Stokes number much smaller than 1, the expression concerns the flow velocities here. Whereas for Stokes number much larger than 1, what you have here is the actual droplet velocities that you have to substitute in these expressions. My focus is not to spend too much time on these expressions. So we use these estimates, and this has been done previously from PDA data to estimate the droplet collision rate by Bori et al. We follow a similar procedure and estimate the droplet collision rate, and again plot it as a function of the turbulence intensity. This is an estimate of the droplet collision rate in the entire field of view that we have made our PDA measurements over. So it's an average quantity, and to our satisfaction, we got a trend that suggested that the droplet collision rates are following a similar trend where there is an optimum turbulence, airflow turbulence intensity at the same value where the droplet collision rate is maximized. So at this point, we were even more convinced that we could just, if we could explain this trend in the droplet collision rates, we would have managed explaining the trends in the droplet size growth rates. So as I said in the beginning of the talk, we're going to say that the efficiency of collisions to coalescence is not playing a huge role in these experiments. Again, these are approximate expressions that we have used for estimating the collision rates. Shyam spent a lot of time analyzing also the long distance microscopy images. As I showed a few slides ago, we took these pictures that are over.
Again, sorry. I'm
yes,
the only guy who's interrupting. I hope it is not a problem.
Absolutely no problem.
Yeah. So the prediction is U cube and U, right? For Stokes. So you are Stokes order 1, is it? Does the prediction fit with the curve? So our collision is not quite toward the rate of collision rate, but I mean the prediction, the theoretical prediction, you can try to fit here. No, I mean.
No. So what we have done is, so our droplet field contains the entire range of Stokes numbers, starting from much smaller than 1 to greater than 1, because it's a polydisperse droplet field.
I see. Okay.
And so this spray nozzles that we have used have a droplet size distribution associated with them. So these are not fixed droplet sizes that we are releasing into the turbulent flow. And what I've estimated here as the collision rate is summation over all droplet sizes.
I see. Okay.
So this is the overall droplet collision rates that we have estimated. So essentially, taken these expressions, here the index I refers to different droplet size bins. And I think intentionally I did not show the dependence on the Stokes number itself for the droplet collision rates, because that's a message that I want to keep separate. But this is an overall collision rate. So and there's no question of whether there was an agreement, because we have just used this expression to estimate the collision rates. At this, we don't have an alternate measurement of the collision rate, but then that's exactly what we thought about, and Shyam analyzed these long distance microscopy images to directly measure the collision rates.
Your fit is very good. Is it, I mean, so good? I mean, that's what I'm surprised.
No, this is not a fit. This is just a trend. We have just joined the individual points.
It's not from theory. The line is not from theory.
No, it's not at all. This is just a trend from the experiments.
Okay, great. Okay, sorry. Okay.
Yeah. So this is not a theory or versus experiments. This is just the trend in the experiments, and I just want to highlight that the experimentally estimated collision rates are following the same trend as the experimentally measured droplet size growth rates.
Okay, sorry. Okay.
As a function of the airflow turbulence intensity. So then an alternate way of measuring the droplet collisions was to painfully go through these individual images, look for droplet collision events, mark them down, and analyze this over 30,000. In fact, I think it's around 10,000 images. I will confirm this at the end of the seminar. But for several thousands of images to actually estimate collision rates more directly. Oh, yes, that's given here. Sorry, 30,000 frames were acquired at 10,000 frames per second. So then we track these individual droplets, and we either visualize the collision event within this frame itself, or there are occasions when, having tracked this trajectory of the droplets, we can estimate that they would collide at some point a little earlier or a little later from the instance of this images. And then we also have to go through quite carefully to make sure we don't double count droplets and so on. But then to focus on the physics and not on the experimental technique, what we did was to plot the collision rate estimate from LDM. So that's the empty circles here. So that's a direct measurement of the collision events. And again, we got a similar trend as a function of the airflow turbulence intensity. So in some sense, you can say this is a comparison between those expressions and the direct measurement of the collision rates. So those expressions are an overestimate. That's what I've pointed out here. And that may have various reasons associated with it. One, those expressions are strictly speaking valid only for very small and very large Stokes numbers. But we have then blindly said at Stokes number 1, the expression just switches from the one due to Landman and Safman for tracer-like particles to the one due to Abrahamson for strongly inertial particles. That could be one of the main reasons, but there is a significant difference between what we directly measure as collision rates and what we estimate using the PDA data. Nevertheless, our focus here is that the existence of the optimum turbulence intensity is present in both these trends. So at least we are able to validate this, the occurrence of optimum turbulence intensity for droplet size growth with the occurrence of the same optimum turbulence intensity for maximizing the droplet collision rates. So then we now move on to thinking about what may be causing these trends in the droplet collision rates. So we have said we have had a trend that we have observed for droplet size growth rates. We have broken it down into saying, okay, if we can explain the droplet collision rates, we will be done. Now thinking about what may cause these changes in the droplet collision rates. The first thing we did was to estimate if clustering is occurring in our experiments. This is again through the PDA data. It's both interesting and challenging to make measurements of statistical measurements of all the droplets that go through a very small probe volume and actually estimate that if spatially extended clusters are present. The way in which it is done is to essentially look at the droplet arrival times in your small probe volume. And if there is no clustering that's occurring, the droplet arrival times would follow a Poisson distribution. And the deviation from the Poisson distribution is a measure of whether clustering is occurring, because when clustering occurs, you would expect at times that several droplets arrive with very small particle separation times in your probe volume. So we make a plot of this pair correlation function, which is a measure of the deviation of the arrival time distribution from Poisson distribution. And it turned out when I was less than or equal to the optimum value that we have reported, the value of PCF was more or less close to 0, right? Which indicates that the droplet arrival times are following a Poisson process. But when the turbulence intensity was to the right of the peak, where it's larger than the optimum air turbulence intensity, then we do start getting significant deviation from the Poisson process, particularly that the small particle arrival times, interparticle arrival times become more likely. So small interparticle arrival times becoming more likely is essentially a signature of clustering occurring in the flow. And so quite interestingly, we have now observed that clustering is a phenomenon that's getting set up at I equals I star. And then it turns out the clustering counterintuitively is actually reducing the droplet collision rates. And we have done a separate set of analysis that shows that, when you, in the clusters observed in our experiments, we essentially have all these droplets moving in a correlated fashion without much collisions between one another. Okay, and another insight that I would like to provide, it's 6:40. So what we also did was to take a more careful look at the droplet size distribution at different axial locations. So in fact, this will show you that it's a really polydisperse droplet field. So at x equals 200 mm, that is the first axial location where we made the measurements. That's the empty circles, and you see the droplet size distribution. On the x-axis is the droplet size itself, and this is the number density corresponding to that bin. And you have a wide range of droplet sizes that are present. Now, as you go to different axial locations, these are all measurements from a single experiment, and you do see a modification of the droplet size distribution. And interestingly, all these distributions seem to intersect at more or less a similar location. So these are droplet size distribution from multiple axial locations. They all seem to have a common crossover point or a crossover diameter. And what's happening for diameters that are smaller than DC, which is the crossover diameter, you have the numbers decreasing, and correspondingly the number of droplets that are D greater than DC is increasing as you go away, as you go to larger and larger axial locations. So what it is saying is, starting from initial droplet size distribution indicated by the empty circles, you have droplet sizes in the range D less than DC on an average, colliding, having collision events, and they contribute to the formation of these larger droplets whose numbers are increasing. So that's indicated here. So if you just look at the droplet size distribution at two different axial locations, the first and the last locations in our measurements, you essentially have a source region that is contributing to these droplet collisions, and they are all colliding with one another. So these droplet numbers are dropping, and correspondingly these large droplets, number of large droplets is increasing due to the collision of these small droplets. So we also plotted this crossover diameter, right? The occurrence of the crossover diameter itself was surprising for us. We didn't expect to see one. And we plotted the crossover diameter as a function of the turbulence intensity. Again, I come back to the same story that there is the same optimum air turbulence intensity for the trend observed in the crossover diameter as well. I would like to point out that the crossover diameter kind of is the maximum diameter up to which these droplets are taking part in collisions, and to the right of the crossover diameter, they are not really taking part in the collisions. They are rather getting accumulated by collisions happening for smaller size droplets. So what seems to our explanation now is that once clustering sets in, you cannot now continue to have this DC increase, because you have these inertial droplets that are present in these clusters that are not taking part in collisions anymore. So once you cross over to the right side of the optimal turbulence intensity, with clustering setting in, the set of particles that are taking part in collisions starts to drop again, simply because the corresponding larger droplets are now belonging to the clusters that form for I greater than I star. So as a summary of the first part, we observed a trend for the droplet size growth rate. We identified the existence of an optimum turbulence intensity. We were able to kind of complement or to make sense of the trend in the droplet size growth rate with a measurement of the droplet collision rates directly and through PDI. And then we explained these trends via the observation that clustering sets in at I equals I star, and the droplet flow field is essentially undergoing this inertial clustering for I greater than I star. And finally, we observed the existence of a crossover diameter, which divides essentially the region, the droplet size, into two separate regions, one D less than DC, which are small droplets contributing to collisions, and D greater than DC, which are essentially the numbers are increasing due to the collision of the small size droplets. What I want to do in part 2 is to now vary the droplet field characteristics and hold the background airflow turbulence at characteristics as a constant. So it's essentially the other way around variation of parameters from part 1, right? Having observed what happens when turbulence intensity is varied in part 1. So the results that I'm going to report in part 2 are reported in an article that's under review. I'll be very happy to share more results or discuss this manuscript if you're interested. Okay, so what do? We now do another set of experiments. There are 11 different cases we run where the background airflow turbulence intensity is fixed. And we, across these cases, we change the initial droplet field characteristics either by changing the spray nozzle itself, or for a given spray nozzle, we change the operating pressure. Both end up contributing to a change in the initial droplet field characteristics. But then one of our challenges was that when we change the spray nozzle, it's not one aspect of the droplet field characteristics that we change, but we end up changing several of its properties. And specifically, we change the droplet number density, which we indicate as rho n, and that is plotted as the last plot here. So rho n as a function of case number. As the case number increases, we are having an increase in the initial droplet number density. But then, unfortunately, the mean droplet size of the initial droplet field was also decreasing as a function of the case number. But I would like to point out, sorry, not in C, in B, the mean droplet size is decreasing. But I would like to point out that as we will go along, I will say that the change in the droplet number density is playing a stronger role. And droplet size distribution is also changing. We choose to quantify the droplet size distribution in terms of a single parameter called the polydispersity, which is the ratio between the outer mean diameter and the mean diameter. So this quantity would be 1 if it was a monodispersed droplet field. And we see that the polydispersity is also changing. But the good news is that it is sufficiently far from 1, or it is sufficiently polydispersed across all the cases. So we are just going to say all the cases are representative of a polydispersed droplet field, and the small change in the polydispersity itself is not playing a big role. So we are going to start seeing plotting various trends as a function of these two parameters in the title, the droplet number density and the mean droplet size. And I repeat, this is going to be for a fixed background airflow turbulence intensity. Okay, at what value do we fix the background airflow turbulence intensity? What we did is, for each of the droplet field characteristics, we Shyam did these experiments of plotting the droplet size growth rate as a function of the turbulence intensity. We observe the existence of an optimum turbulence intensity for each of these droplet field characteristic cases. So then we identify this maximum droplet size growth rate R star, and the corresponding turbulence, optimum turbulence intensity is I star. So you see these trends from the different cases. So finally, I'm going to, from this entire distribution, just pick up the droplet size, the maximum droplet size growth rate, and plot it as a function of the initial droplet field characteristics. The optimum value for the turbulence intensity itself did not change much as a function of the case number. So it turned out for each of these initial droplet field characteristics, we did experiments at a fixed background airflow turbulence intensity of the value that is indicated here, around a little more than 14%. Okay, so what are the trends we observe? Like for part 1, we just first plot the trend of the maximum droplet size growth rate as a function of both the mean droplet size in the droplet field and the droplet number density. These are also characteristics associated with the initial droplet field that we are generating from the spray nozzle. I will repeat that these are the same 11 experiments. Is it 11? Let me just confirm. Yeah, these are same in both the plots. Unfortunately, we had both D bar and rho n varying simultaneously. So we plotted the trends both with respect to D bar and rho n. And a couple of things to point out. One is that let's look at the plot on the right. The droplet size growth rate as a function of rho n seems to be more or less a constant for the first 6 cases or so. And then at some threshold value of the initial droplet number density, it starts to increase quite rapidly as a function of rho n. And you see that the increase is indeed quite rapid compared to this region. And similarly, you can interpret it as when the droplet mean diameter becomes smaller than some value, it starts to increase quite rapidly. But I would like to point out that the change in the droplet number density in this last 4 or 5 cases where this rapid growth in the droplet size growth is observed, the change in the droplet number density is more appreciable than the change in the mean diameter of the initial droplet field. This is going from around 21 microns to 20 microns for these last 4 points, whereas there is a change in the droplet number density by at least a couple of 100 per centimeter cube in the last 4 or 5 cases. Okay, so our intuition was that the droplet number density is playing a stronger role and contributing to this rapid increase in the droplet size growth rate. Okay, to understand these trends, we again go back to the LDM or the long distance microscopy images. This involved even more painful analysis of these individual images. And the first observation is that we observed 3 different kind of droplet pairs. So you see within this white box, you have one droplet pair, and we observed 3 such droplet pairs. The first I'm going to refer to as the continuous correlated pairs. When I say continuous, the droplet pair contains 2 small droplets whose Stokes numbers are both smaller than 1. And they're correlated, by which I mean that they are going to move more or less with a similar velocity. And so they are, even though they are quite close to each other, they are not really going to collide, at least within the frame that we have captured. So they are correlated and continuous. Continuous referring to the fact that both droplets are of small sizes. Correlated referring to the fact that they are more or less moving together. Another class of droplets pairs that we observed was these caustic pairs, where you have within the pair one being an inertial droplet of Stokes number greater than 1, and another being very small droplet size. We have tracked these 2 individual droplets, and at a later time, around 1 millisecond later, you have the 2 droplets being close to each other. These are referred to as caustic pairs, and caustic pairs always result in collisions because a Stokes number greater than 1 inertial droplet and a Stokes number smaller than 1 droplet are always going to have a relative velocity with respect to one another. So all the caustic, or most of the caustic pairs, result in collisions within the frame that we have captured. And the final class of droplet pair we observe are continuous uncorrelated droplet pairs. So continuous because the droplet sizes are again similar and Stokes corresponding to Stokes number less than 1, but they are uncorrelated. So in the sense that even though they are of similar size, they end up actually coming close to each other in this specific instance and finally result in collisions. Okay. And what did we do? We plotted histograms of the number of these continuous and caustic pairs as a function of a parameter S that we defined. Okay, small values of S. I would please request you all to ignore the plots in A and B. Let's just focus on the plot in C. What is plotted on the x-axis is this parameter S, which essentially for small values of S, it corresponds to continuous pairs, which contain droplets of similar sizes and Stokes number less than 1. And large values of S correspond to a caustic pair, where the droplets, one is an inertial droplet with Stokes number greater than 1, and the other is a relatively small sized droplet with Stokes number less than 1. Okay, within these continuous droplet pairs, we observe both correlated and uncorrelated. Correlated pairs don't contribute to collisions. Uncorrelated pairs contribute to collisions. And as far as caustic droplet pairs are concerned, they are always uncorrelated and hence contributing to collisions. So what we did here was to try and estimate the fraction of each of these classes of droplets, droplet pairs. One is the small value of S corresponding to continuous droplets. Here the 2 different colors correspond to the cyan color corresponds to those that are contributing to collisions, and the dark blue color corresponds to the fraction that does not contribute to collisions. And the first thing I would like to point out is that the droplet pairs are essentially bimodal in distribution. We can either classify them as continuous or caustic pairs. And as you increase the case number, the droplet number density is increasing. And as the droplet number density is increasing, it seems like the fraction of the continuous uncorrelated pairs is increasing. Continuous corresponding to two small droplets within a droplet pair, uncorrelated because they are contributing to collisions indicated by this color. So please note that the axis numbers are different in C and D. So as for case number 8, if you compare it with the number of small droplets that are contributing to collisions, the small droplet pairs, it's larger for case number 8 than case number 3. Okay, so we finally plot first the fraction of uncorrelated pairs as a function of the droplet number density. Uncorrelated pairs are essentially all the droplet pairs that are contributing to collisions, and that is increasing and also rapidly increasing beyond the previously identified threshold value of the droplet number density. But then more interesting is the plot on the right, where we divide the colliding droplet pairs into contribution from the continuous droplets and the caustic droplet pairs. And you see that the rapid increase in the droplet size is essentially due to the increase in the contribution to collisions from the continuous droplet pairs, which have similar sized small droplets within the pair. And correspondingly, the contribution to collisions from the caustic droplet pairs is almost constant with respect to this increase in the droplet number density. So then we went after explaining this mechanism of why the contribution to collisions from continuous droplet pairs is increasing. First, it's already interesting that continuous droplet pairs are contributing significantly to the collisions. But two, the question is, why is it suddenly increasing beyond the threshold value of the droplet number density? This we explain essentially by observing that several of these continuous droplet pairs are encountering a large inertial droplet in their neighborhood. Okay, so what we observed in our analysis of all the LDM images is that there were some droplet pairs that were encountering a large inertial droplet in this neighborhood. This occurrence, close encounter of inertial droplet, is introducing fluctuations in the velocity of the small droplet pair, and which in turn makes this continuous droplet pair uncorrelated. Okay, so that's what we finally plot in the rightmost plot here, where we are plotting a measure of the closest encounter with an inertial droplet on the y-axis as a function of the droplet number density for all these continuous droplet pairs. And indeed, there's more close encounters of inertial droplets that we observe at beyond this threshold value of the droplet number density, beyond which we saw that the droplet size growth rate rapidly increases with droplet number density. So as a summary, we had two different parts. The first 2 points corresponds to part 1, where we said for a given initial droplet field characteristics, there exists an optimum air turbulent intensity that maximizes the droplet size growth. And we explained it via the observation that clustering is onset at I equals I star, and it exists for all values of turbulence intensities greater than I star. And this clustering actually suppresses the droplet collision rates. In the second part of the talk, we fixed the background air turbulence intensity and changed the droplet number density in the initial droplet field. And we observed a rapid increase in the droplet size growth as a function of the droplet number density. And the mechanism that we attribute to this trend was essentially that beyond the threshold value of the droplet number density, these small sized droplet pairs encounter more and more of these inertial droplets in their neighborhood. And once they encounter these inertial droplets in the neighborhood, those inertial droplets induce strong velocity fluctuations in these small droplets pairs, which makes them uncorrelated and finally contributes to collisions within this continuous droplet pairs. We have done a little more work to see if these conclusions fit in with some of the observations for warm rain initiation. I'm happy to discuss it more offline. That would be too much content for this seminar. I'm happy to take any questions now. Thank you.
Okay, thanks, Mani, for the wonderful talk and experiments.